learners, it's Em from Sononerds, and this video is on Unit 17A, Tissue Harmonics. Unit 17A, Tissue Harmonics. So tissue harmonics and contrast agents both rely on the ideas of non-linear behavior. And when the nonlinear behavior is the result of a sound beam interacting with a soft tissue, tissue harmonics are created. And when the nonlinear behavior is the result of sound beams interacting with the bubble, contrast harmonics are created. So even though these two ultrasound advancements have very similar concepts that are integral to superior diagnostic imaging, their physics discussions look a little different. So Unit 17 has been split into Unit 17A, which will be tissue harmonics, and then 17B, which will be contrast harmonics. So let's go ahead and get started then with tissue harmonics and section 17A.1, fundamental and harmonic frequencies. When a sound wave is created, the waves are going to propagate in a very smooth, predictable manner, and we represent it with a sinusoidal waveform that looks a lot like this. However, as the sound interacts with the media that it's propagating through, we see the waveform start to transform. Due to pressure changes, we begin to see that compressions are going to start to travel a little bit faster, and rarefactions travel a little bit slower. This is going to create a non-sinusoidal waveform that looks a lot like this. So remember, the compressions travel faster and the rarefactions travel slower. And this is because as the compressions travel through, they're going to move those molecules a little bit closer together. And when that occurs, it causes the media to become a little bit stiffer. And then we will see that through that stiffness increase, we see a propagation speed increase. So again, compressions are going to travel a little bit faster, where the rarefactions are going to travel just a little bit slower. Same idea, the stiffness has been reduced during rarefactions. So when the waveform is predictable or behaves in a linear pattern, this is going to be the fundamental frequency. The fundamental frequency is what we expect is being emitted by the transducer. Very predictable lines. Think of trains, think of the subway, very predictable. Whatever the transducer is labeled is what we expect to come out. That is the fundamental frequency. That is going to be producing a sinusoidal waveform as it comes out of the transducer. However, when the waveform becomes unpredictable or nonlinear, a harmonic frequency is created. And those harmonic frequencies are derived from the fundamental frequency. Harmonic frequencies are going to be multiples of the fundamental frequency. They come in odd and even harmonics, and it's as easy as just multiplying the harmonic by the fundamental frequency. So for example, if our fundamental frequency is 2 megahertz, second harmonics is 2 times 2, which is 4, and that is an even harmonic. Third harmonics is an odd harmonic, 3 times 2 is 6, so the third harmonics are 6 megahertz. Fourth harmonics, again, are an even, 4 times 2 is 8, fifth harmonics again are odd, 5 times 2 is 10. So if we were to use some sort of wave analysis and we are able to pick apart the different frequencies that are being created by these compressions traveling faster and the rarefactions traveling slower, we would be able to find different frequencies on the ordinance of that 4, the 6, the 8, the 10, different harmonics being involved in creating these different waveforms that are non-sinusoidal. The other really big thing about tissue harmonics is that these harmonics are created in the tissue. That's why they're called tissue harmonics. So as the sound beam leaves the transducer, there's no harmonics yet. Nothing has been created harmonic-wise. This is all fundamental frequency. So we've sent a 2 megahertz wave into the body. As that wave propagates through the tissue, the echoes that are coming back are going to be a 2 megahertz, a 4 megahertz, an 8 megahertz. It's going to send multiple harmonic frequency echoes back to the transducer. So it's created in the tissue as the sound propagates. It changes how those compressions and rarefactions propagate through the tissue, and that is how we get those extra frequencies, and those are the frequencies that are also going to return back to the transducer. Remember, all sorts of frequencies are coming back. Whatever our fundamental frequency is going in, once it starts to interact with the tissue, it's going to send different harmonic frequencies back. So I have 4 key things that I want you to remember about harmonic frequencies. The first one is that harmonics are created in the media. For ultrasound, that's the body, so the tissue. Tissue harmonics are what we are talking about. Secondly, harmonics are non-linear or unpredictable. So that faster and slower, it changes depending on the media that it's going through. It changes depending on a lot of things. So there's really no predicting how the compressions are going to behave versus how the rarefactions are going to behave, but we know they're going to change speed. They're unpredictable. Remember that harmonics are multiples of the fundamental frequency. So we have second harmonics, 2 times your fundamental. Third harmonics, 3 times your fundamental. Fourth harmonics, 4 times your fundamental. Harmonics are going to be multiples of the fundamental frequency. And lastly, the less sinusoidal that waveform becomes, we see stronger harmonics being created. Section 17A.2, Tissue Harmonics. So let's look at the physics behind tissue harmonics. When the sound wave enters the body, it's going to start to change shapes. And as that sound wave continues to propagate through the body, the harmonics, which are deforming the waveform, are going to become stronger. So what we end up seeing is in the near field, we're just starting to interact with the tissue. So we're going to see very little change as the sound really hasn't had a whole lot of time to propagate through that tissue. In the midfield, we're going to start to see more harmonics being created because we've had more time to interact with the tissue. And then finally in the far field, we see the strongest harmonics being created because it's had a lot of interaction with the tissue. So harmonics get stronger as we get through the media. As it travels through the tissue, stronger harmonics occur. The problem is, though, is that when we get to these really strong harmonics, they tend to attenuate too quickly before we can use them. Remember, our stronger harmonics are going to start showing up as the 10, the 12, the 14 megahertz. And we know that higher frequencies attenuate. So when we're getting into our very strong harmonics down here, we would expect better pictures, except we're fighting that attenuation piece of it. So what we end up seeing is that the best harmonics for our pictures tend to be in that midfield. We're getting just enough distortion of the fundamental waveform to start to get those harmonics. It's not too much to the point where it's going to attenuate before it can make it back to the transducer. And it just so happens that a lot of times what we're interested in happens to be in the middle of our picture as well. So the best harmonics for imaging come back from the midfield. The strongest harmonics come back from the far field, but we can't use them due to attenuation. And in the near field, we really don't get much for harmonics, maybe a little bit. The best part about this is that there's really less distortion in that near field, and I'll show you some examples of that in a minute here. This graph is another way of showing how mid-range depths tend to produce more harmonics, and that has everything to do with the fact that the fundamental frequency is continuing to interact with tissue as it enters into the body. So let's look at this dotted line first. This is the fundamental line. As the fundamental frequency comes out of the transducer, it's a really strong beam. It's a strong energy sound wave. So it's got a lot of strength. Right as it comes into the body, it starts interacting with the skin and the adipose layers, and there's just a lot of interaction right in those first few centimeters that we lose a lot of our sound energy almost right away due to attenuation. And we're going to see continued attenuation as the sound wave travels deeper and deeper into the body. But we just learned that as that fundamental beam interacts with the tissue, it creates more harmonics. So even though that fundamental beam is attenuating, its interaction with the tissue is creating those harmonics. So we don't see a whole lot of harmonics being created right away because it's just starting to interact in those first few centimeters. We'll see a lot more interaction with tissue, kind of in that mid-range, and that is where we're going to see our best harmonics. Now we do see more harmonics being created, but they're starting to be attenuated way too much at this point. So in your very far depths of your picture, harmonics are strongest, but they're never going to make it back to the transducer due to their attenuation. This graph also helps to point out the fact that if you are imaging very deep, you are probably better off using a fundamental frequency because you will still experience less attenuation of your sound wave in that far field, compared to harmonics. So if you're imaging to a moderate depth, harmonics is going to make for an awesome picture because harmonics does improve the signal to noise ratio in that mid field, but fundamental frequencies are going to remain stronger throughout the depth of the picture and sometimes might prove helpful for those really large, deep images on certain patients. So the big things to take away from this image is remember that fundamental frequencies attenuate very, very quickly, not to the same degree as harmonics, but they do attenuate very quickly. And it's that attenuation, that interaction with the tissue, is what's creating our harmonics. And we see the best harmonics kind of in that mid-field depth. Too much attenuation as we get into those deeper depths. I also want to point out that strong beams are required for harmonics to be created. So with this in mind, it makes it really important where we place our focus because we know that the focus, or at least the focal zone, really is the strongest part of the beam. So we want to make sure that we're placing our focus at our area of interest so we get the best harmonics at the area that we're interested in. And harmonics improves our image. So we're going to see stronger harmonics produced around the area of focus. Stronger harmonics are going to improve our image because we are improving the lateral resolution. We're seeing a lot of really good things coming from the focal point in combination with harmonic imaging. So speaking of harmonic imaging, let's take a little bit closer look at what harmonics imaging actually is. Now, if you recall back to learning about our system components, we talked about in the receiver, one of the functions being amplification. And there was a first amplification that occurs where the machine just has to make the signals bigger so the receiver can process them. So during the first amplification, signals are coming back to the machine component, the amplifier. And the amplifier is going to be tuned or keyed in to certain frequencies within the bandwidth that's created by the transducer. Remember, our bandwidth is based on the backing material. If we have a 12.5 transducer, that means it can produce frequencies as low as 5 megahertz and up to 12 megahertz. And that's what the amplifier is tuned into. It's got the bandwidth 5 to 12 in mind. And with the amplifier, it is going to ignore everything outside of that 5 and 12. Anything below 5 is really going to just be considered noise. Anything above 12 might also be noise or interference from other things. So the amplifier is really focused on the bandwidth of the transducer. It can even go a step further then and kind of start to ignore other frequencies, even if they're coming back within the bandwidth. So we can see in this example here, the fundamental frequency was sent in, 2 megahertz went in, and what came back were a bunch of different frequencies. Maybe a 1 megahertz came back, maybe that's some extra noise from outside of the body. The 2 megahertz echoes are definitely going to come back. We're getting our second harmonic and our fourth harmonics are coming back. So these are the examples that we're using. Now, if we're using harmonic imaging, the amplifier then is going to say, nope, I don't want 1 megahertz echoes. I don't want 2 megahertz echoes. I don't want those 8 megahertz echoes. I'm only going to let the 4 megahertz echoes travel through. I'm going to amplify them, and those are the signals that this image is going to be made from. So 4 megahertz passes through the amplifier, gets amplified, and that is what is processed to create our image. So with harmonic imaging on, the machine is listening for those second harmonics. It's going to let them through, and that's what's going to make our picture. So the amplifier is tuned to the second harmonic. It's going to ignore all the other echoes coming back and only allow echoes that fit the harmonics bandwidth to be processed further by the machine. I want to point out that typically when we are talking about harmonics, even though we have second, third, fourth, fifth harmonics, the machines are almost exclusively listening for second harmonics. So if 2 megahertz went in, it's usually only listening for 4 megahertz. And the reason for that is because there really needs to be a narrow bandwidth. If our bandwidth is too wide, we are going to start to ignore some of our harmonic frequencies. So we don't want too much overlap between our fundamental frequency and the harmonic frequency. And so with that, we tend to only listen for the second harmonics. Now, why do we want to use harmonics? I've mentioned it in a couple spots already, but the use of harmonic signals is really going to improve our image, and it's going to improve our image in 3 particular ways. The first one being that the harmonic beam is super narrow, and we know that when we are using a narrow sound beam, that's going to improve our lateral resolution. So not only are we getting improvement from the focus creating strong harmonics, we're also getting super narrow beams at the focus, which improves the lateral resolution. Secondly, grading lobes and any artifacts that come from those are typically eliminated because only strong beams can create harmonics. Remember, grading lobes were the extra little sound information that's kind of escaping the main beam in our array transducers. So those extra kind of weak sound beams, when we're imaging in fundamental, they're going to send back fundamental echoes. But when we're imaging in harmonics, they can't produce harmonics. And so those echoes coming from that side part aren't even processed by the machine. And lastly, what we end up seeing is because harmonics really aren't created in those first few centimeters, we tend to get really nice near fields because the fundamental frequencies are going to distort a whole bunch in that near field where harmonics can't because they haven't really been produced yet. And I've got an example that I want to show you where we can look for these three improvements. So on top here, we have our fundamental image, and on the bottom, we have our harmonics image. Now, one of the first things that I want to point out is that we have a 67% gain on our harmonics and a 55% gain on our fundamental. What this means is that we had to turn the gain down really far on the fundamental image, most likely to get rid of those grading lobe artifacts, kind of that extra noise that's in the picture. We wanted to get rid of that, probably had to turn the gain down. The next thing that I want to point out is that near field. Look at the fundamental near field. See how blurry it is and kind of fuzzy? We're getting a lot of distortion because remember that really strong sound beam is coming in, interacting with the layers of the skin. It's attenuating a whole bunch up here. It's getting very distorted. Not a good picture in the near field. But look at our harmonics picture. We can actually see the skin line. We can see the next layer down. We can see individual echoes through here. We are seeing just a much crisper, cleaner near field. Another thing that we are seeing benefit-wise then is improved lateral resolution. If we look at just the pictures in general, we're seeing much crisper borders in our harmonics. The specular reflectors are very, very smooth. We're seeing a lot of tissue differentiation that comes from that lateral resolution piece of it. We're really just seeing a cleaner, crisper image. It is visually more appealing, and if there was pathology, that pathology would be much clearer as well. So when it is feasible, use your harmonics imaging, but know when it's time to switch back into fundamental imaging as well. When we started talking about how harmonics imaging occurs using the amplifiers and kind of filtering out the different echoes, I want to note that when we do that, the axial resolution has to degrade. And that is because, remember, the machine wants narrow bandwidths. And to get those narrow bandwidths, we have to have longer pulses. And longer pulses means a longer spatial pulse length, which means a higher axial resolution value. So when we have a narrow bandwidth, we degrade our axial resolution, and that is the best way for the filtering process of harmonics to occur. But of course, we really don't want that. We want all the benefits of harmonics, but we don't want to lose out on our axial resolution on top of it. So what most machines use is something called pulse inversion harmonics. And the pulse inversion harmonics is going to improve the process so there's no loss in axial resolution, and it follows kind of a step-by-step process. So first, the machine is going to send 2 pulses down each scan line. They're both going to be of fundamental frequency, and they're going to be 180 degrees out of phase. They are going to interfere with one another, and when they are 180 degrees out of phase, it means that they are going to 100% destruct. And that's important for this pulse inversion harmonics. So 2 pulses sent down each scan line. The fundamental waves then are going to create those harmonics in the tissue. They're both going to create harmonics. As the echoes return from the fundamental waves, as I mentioned, they're going to 100% destruct. They are going to cancel each other out. So the fundamental echoes cancel each other out. And what we're left with are harmonics from both of the waves. And the way that they come back, they actually end up being 100% in phase. So they are going to construct, thus doubling their size, making their signal stronger, which makes the harmonic signal stronger for the machine to use. So it's like all over bonus, bonus, bonus. We're getting rid of those fundamental echoes. We're doubling the size of our harmonics echoes, but we are sending 2 pulses down every scan line, so we're going to see a change in temporal resolution. So just as a visual again, 2 megahertz pulse is sent in. We're also going to send in 180 degree out of phase 2 megahertz pulse. And then those echoes are going to come back, and because they're 180 degrees from one another, they are going to cancel each other out. However, there's still going to be a 4 megahertz harmonic echo returning from both of the fundamental echoes. When you have those two 100% lined up, they double and make a stronger 4 megahertz harmonic wave. So again, pulse goes in, 180 degree pulse also goes in. Remember, 2 pulses per scan line cancel each other out. The fundamentals cancel each other out. Harmonics from one wave come back. They combine with the harmonics of the other wave. That combination is a construction. They're going to double in size, making it a very strong wave. So like I said, with those 2 pulses going down every scan line, we do see that pulse inversion harmonics is just going to very slightly decrease the frame rate, which degrades our temporal resolution. And we can see that in our images here. We have no harmonics on in this image, and we do have harmonics on in this image. The frame rate in this one is 51 hertz. The frame rate in this image is 47 hertz. So remember, anything above 30, our eyes kind of see as a movie. So really it's a minimal change, but it's a change nonetheless when harmonics is used. Just looking at these pictures again too, this is of the thyroid, so we're using a very high frequency transducer as it is. But notice again, we're getting a lot of distortion through this near field. We're getting a lot of blurriness through the thyroid tissue itself. This carotid artery here has really, really fuzzy borders, kind of looks really junky in there. This vessel looks very junky. This is the other carotid. The muscles looks like they have like shadows in them. It's just not a very pretty picture compared to our harmonics picture, which has really crisp lines. We're getting really nice borders on our vessels. We're seeing just a lot more detail in the tissue itself. So again, anytime you can use harmonics, use it as long as the temporal resolution piece of it is not an issue and being able to image far enough into the body is not an issue. So pulse inversion harmonics really are more commonly used by current systems. But there is another method by which harmonics can be created, and that is through something called power modulation harmonics. So power modulation harmonics kind of follow the same idea. It has like a recipe or a step-by-step that it needs to follow. It just goes about it in a little bit different way than the pulse inversion. So first, a very weak beam is emitted. And remember that weak beams cannot create harmonics. Really only strong beams can. So of course, we need to send a strong beam down as well. The strong beam is going to be 2 times stronger than the weak beam, and it's going to be the same frequency as the weak beam. That's important. Next up then, the fundamental echoes are going to return. So weak beam fundamental echoes return. The strong beam fundamental echoes also return. And when they return to the machine is going to take those weaker beams, double them, and now it's going to know which echoes to ignore because that weak beam doubled should match up with the echoes that came back from the 2 times stronger beam. What's left then are just the harmonics that were created by the strong beam, and those are the ones that are going to be processed for the image. So I have a visual representation of that as well. So remember, weak beam is sent in, a 2 times as strong, same frequency beam is also sent in. So we're using 2 pulses again per scan line. Those pulses are going to go into the body. Only the orange one, the strong beam, can create harmonics. So fundamental echoes come back from the strong beam, fundamental echoes come back from the weak beam, and the strong beam harmonics come back. Once they get back to the machine is going to double the purple one. So it figures out what matches up with the orange echoes. It's It's going to cancel all those out, and all we have left then are the harmonics that were created by the strong beam. Those then are used to produce the image. And that is tissue harmonics imaging. So remember, tissue harmonics are created in the tissue. Fundamental frequency leaves the transducer. The interaction of that sound beam in the tissue creates the harmonics. Most machines are going to use the pulse inversion technique, so be aware of how that works with using waves that are out of phase from one another. You should also know then how and why harmonics improves our images and why we would want to use them in certain settings. You do have a few activities in your workbook and of course your nerd check questions to review the content that we just covered.